Good afternoon, everyone. So we'll start. We'll discuss one of the topic of the optical communication system, optical communication. That is the efficiency of LED, or we'll derive the equation for the efficiency for calculation of the efficiency of LED. My name is Himanshu Nagpal, assistant of professor in EC department of AKGEC Ghaziabad. So before we start with the efficiency of the LED, we should know about the working principle of the LED. So that is a spontaneous emission. That is a working principle of LED, and in the spontaneous emission, there is a concept that is a absorption. First one is the absorption, and second one is the spontaneous emission. So we'll see that if I say this is a PN junction diode which is in the forward bias direction, which is connected the. So mainly recombination takes place in the this active region, that is in the depletion region. Mainly recombination takes place in this region, and through this the light will be emitted. So the recombination of electrons and the hole pair generates what? Generates the photon, and this photon gives us the, if this wavelength of photon which is released is in the visible region, then I can say that the light is emitted But if the recombination takes place and the photon is not generated and the heat is generated, that type of recombination we generally known as the non-radiative recombination. Clear? Now start with the absorption. Now let's say this one is the valence band and this one is the conduction band. This one is the conduction band, and this one is the valence band. Now if I say initially electron is placed at the valence band, on getting energy, this electron will jump from valence band to the conduction band. Clear? And on getting energy means on absorbing the energy, so that's why it is known as the absorption. Now this electron will be at this point, and that is at the conduction band. Now if I say for achieving a stability of a system, this electron will automatically, remind, that is this electron will have its lifetime, or it will get automatically comes back to the valence band. So that type of emission, and it generates what? It generates a photon. So that types of, it generates some energy in the form of photon or heat energy. That types of emission is known as the spontaneous emission. Clear? Now if I say from this point to this point, recombination takes place in this is a PN junction, P and N. Recombination generally takes place in this direction. Mainly the recombination takes place in this area, means electron density will be reduced within time, with some time. Electron density will be after recombination. This point to be noted, the electron density will will decay, will reduce or decay with some time after recombination. So we'll see the first point, that is the efficiency of LED, and this efficiency is further divided into 3 to 4 types, that is a internal quantum efficiency, second is external quantum efficiency, power efficiency, coupling efficiency. So there are number of efficiency we will discuss in the efficiency of LED. So you will see here, to be noted that the photons which electrons which is enter into the after recombination get decays after some time, clear, due to the recombination, and after recombination photon will be produced. Now see, there are two types of recombination of electron and holes. On recombination, there may be a generation of photons, and after recombination there may not be a generation of photons, only heat energy will produce. So this type of recombination in which the generation of photons will take place, in this type of combination is known as the radiative recombination. And here, in which the heat is not generated and the heat is generated, that type of recombination is known as the non-radiative recombination. Clear? Now see, now I'll start with the efficiency of LED. This is the basic prerequisite which you should know about this one. Now first one is the internal quantum efficiency. This internal quantum efficiency is equal to what? If I say that is quantum, means in terms of photons and electrons की बात करेंगे, this internal quantum efficiency will be equal to what? Output by input. And what is the output? Number of photons generated internally divided by the number of electrons injected, and this injection of electrons will be by the forward biasing of the LED. ठीक है, when we connect the PN junction in the forward biasing direction, and that means we are injecting the number of electrons. So quantum efficiency is known as the ratio of photons generated to the injected electrons of the device, that is known as the internal quantum efficiency. Now talk about how much power is generated by the LED will be given by what? How much number of photons will be generated by the photons, that determines the power generated by the LED. Now how many number of photons will be generated, that depends on the how many number of electrons will be recombined in the P and the N region, in the depletion region of PN junction diode. Clear? So that type, how many electrons will get recombined, means we should know about the how many initial number of electrons. Let's say initial number of electrons which is injected, which is in the p-n junction diode, that is delta n naught. Clear? Or let's say this is, yes, delta n naught, that is the initial number of electrons, excess initial number of electrons. Clear? And after recombination, this excess electrons, yeah, this excess electron density which is we are injected into the optical fiber, into the in the p-n junction diode, yeah, in the LED, this excess electron will be decayed on recombination, and this decay of electron will be in the exponentially, decay, because it depends on the lifetime of the carrier. Clear? So the excess density of electrons initially, let's say delta n is equal to delta p is equal, since the injected electrons, injected carriers are created and recombined in pairs such that the charge neutrality will be maintained within the fiber, within the structure. So in the extrinsic material, when you have doping, one carrier type will have a much higher concentration than the other, and in the p type generation, let's say in the p type, the whole concentration will be higher as compared to the electron in the p type region. So I have already told you that this excess carrier density which is exponentially decay with time, means this excess carrier density, that is electron or photon, electron or hole. So this electron density, initially let's say electron density is delta n naught. So electron density will decay, that is rate of change of electron density, that is delta n, will be equal to delta n naught exponentially e power minus t by tau, and this tau is the lifetime of electron. Clear? So delta n naught is the initial injected excess electron density, and this is a t represents the total carrier life recombination lifetime, and tau is the lifetime of the electron. Clear? So only delta n is only a small fraction of the majority carrier that comprise of the minority carriers. It is a constant. If I am providing a, this is a, let's say this is a LED and p and n, when I am providing a forward biasing, there will be a constant current flow into the junction and the equilibrium condition is maintained after some time. Now see, the total rate at which the carriers are generated will be equal to what? The total rate at which carriers are generated, means total rate at which photons are generated, will be equal to what? Will depends on the recombination, and that recombination is depends on the number of electron density, and how many, that means the total rate at which carriers generated, that is equal to number of electrons supplied, externally supplied, that is sum of the externally supplied electrons and the thermal generation rate. कितने हमने सप्लाई कर रहे हैं इलेक्ट्रॉन, और उस इलेक्ट्रॉन में से कितने क्या हो रहे हैं, थर्मली जनरेट करें, उसी से तो मुझे फ्रॉम दैट आई कैन सी दैट द कितने नंबर ऑफ फोटॉन्स जनरेट हो रहे हैं. मींस अ रेट ऑफ इक्वेशन फॉर द कैरियर रिकॉम्बिनेशन कैन बी रिटन एज d by dt delta n. This delta n electron density, decay of electron density. This decay of electron density automatically tells us that the how many number of photons will be generated, that is equal to thermally electrons, injected electrons, that is J by ED, minus में after recombination how many electrons will get will be recombined, clear, that is delta n by tau. कितने नंबर ऑफ इलेक्ट्रॉन्स बचे हैं, कितने बचे हैं, दैट मीन्स कितने आपने सप्लाई कर रहे हैं और कितने रिकॉम्बिनेशन में चले गए हैं, दैट इज जे बाय ईडी माइनस में डेल्टा एन बाय टाउ. नाउ सी दिस इज अ recombination and this recombination will be what, consist of radiative and the non radiative, radiative plus में non radiative, clear. Now see, if I say for the steady state condition, for the steady state condition means जितने electrons you are providing and उतने क्या हो रहा है, रिकम्बाइन कर रहे हैं, जितने आप इलेक्ट्रॉन्स दे रहे हैं उतने ही क्या कर रहे हैं, रिकम्बाइन कर रहे हैं. मीन्स दिस डी डेल्टा रेट change of electron density with respect to time will become equal to 0. When this becomes equal to 0, for means that is the steady state equation, this become equal to 0, that means J by ED, J by upon में ED will be equal to what, delta n by tau, and you can see that delta n comes out to be J by ED multiply में tau. Now this defines what, thermal generation rate means recombination rate, and this recombination consists of recombination rate, this consists of what, this consists of what, radiative plus में non radiative. So you can see that the recombination rate, that is if I say this is RT, that is recombination rate, total recombination rate will become equal to J by ED, that is this one, that is RT equal to J by upon में ED. This recombination rate consists of what, recombination, radiative recombination rate, radiative recombination rate प्लस में नॉन रेडिएटिव recombination rate. Now as we know that the total number of recombinations will also depends upon what, how many electrons will is injected and how many number of electrons will is injected, that can be defined as the current which is supplied divided by the electron charge, that is RT, and this RT is also what, consists of what, radiative recombination plus में non radiative recombination, clear. Now internal quantum efficiency is equal to what, you know that the internal quantum efficiency is equal to what, number of photons generated upon में number of electrons injected. It means how many number of photons generated, that is the radiative recombination. I can say that this is equal to RR, radiative recombination rate, divided by the total number of electrons injected, that means the total number of recombinations rate, because in the steady state condition I have already told you, if I say steady state condition में जितने number of electrons आप दे रहे हैं उतने recombine कर रहे हैं, it means कितने number of electrons दे रहे हैं means उतने recombine कर रहे हैं, that is equal to RT. So this one is equal to internal quantum efficiency, and this is, can also be written as RR by RT, clear. So this internal quantum efficiency can also be written as RR upon में RR plus में R and R. So this is one of the formula for the internal quantum efficiency. Now the another formula can be written as, that is, as we know that this is equal to RR upon में RT, and this is what, RR upon में RT is equal to what, I upon में E. So it means the RR equal to what? From this equation you can see that this RR is equal to what? Internal quantum efficiency, sorry, this is internal quantum efficiency, ठीक है, this is internal quantum efficiency multiply में ये उधर चला गया, that is I by E, that is this one, this is I already told you. Now if I want to calculate the how much power is generated internally, now अभी हमने क्या पता लगाया था कि कितने photons generate हो रहे हैं. Now if I want to calculate the internal power generated by the LED, that will be equal to what? Number of photons generated multiply by energy of photons, from where I can calculate the how much power is generated, that is P internally, how much power generated internally, that is energy of photon multiply by number of photons, that is radiative generated per second. That means equal to energy of photon is equal to what? H into में nu, this is internally power generated, H into में nu, and how many number of photons generated, that is radiative, that is multiply में RR, as we know that H into में nu, from here you can see that the RR equal to internal quantum efficiency, that is internal quantum efficiency multiply में I by E, clear, and this is equal to H nu is equal to Hc by lambda multiply में internal quantum efficiency multiply में I by E, that is equal to internally power generated, clear. Now see, this internal quantum efficiency can also be described in terms of what? Recombination lifetime of the carrier, clear. So as we know that the internal quantum efficiency is equal to what? RR upon में RR plus में RNR. Now if I want to calculate in terms of the lifetime of the carrier, means I can say written as 1 upon में 1 plus में RNR upon में RR, and this can also be written as 1 upon में 1 plus में tau R divided by tau NR. So internal quantum efficiency can also be defined in terms of this one, that is equal to tau NR upon में tau R plus में tau NR, clear. So in the next lecture we will discuss the further efficiency of the LED. Today I have discussed about the internal quantum efficiency of the LED and the internally power generated by the LED. In the next lecture we will discuss about the external quantum efficiency, external power efficiency, and the coupling efficiency. Thank you. The book which I have prepared for preparing this slide, that is Optical Communication System by John M. Senior.